This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning, everyone. Happy to see you. All right. We are continuing today the lecture from last Friday, and it was brought to my attention that it would be good to have a 2-minute silence in the middle of the lecture for the events in New Zealand. I will observe that because I do respect the traumatic happenings around the world of some extreme opinions or brainwashed people taking guns, let's say, and doing whatever they feel like. So before then, that will happen in like almost half an hour. Before then, let's start. Let me remind you where we roughly ended last time. Let's see. So I gave you, first of all, this example. Yeah. In this example, I was doing a time derivative of a vector. Sorry, I forgot to put the pointer. We look at this vector, AB, and we think of its derivative in time, how it changes over time. So we prepared this vector in 2 different frames. The red frame 1, which is moving together with this disk or with point B, you can think of it like that. And also we prepared this vector RAB in frame 0. Okay, frame 0, the black one, which is stationary, doesn't move. And then we attempt to take a derivative. First, we do what I call term by term or component by component derivative. And I said, when you do this component by component derivative in a frame like 0 that is not moving anywhere, this is fine. So here I can really put this little dot. You see the dot here? This dot means this is the derivative in time, or the actual change over time of this vector RAB, and this is fine. However, if we attempt to do the same in a moving or non-inertial coordinate system, like 1, we are getting something wrong, and we need to resolve that issue. Okay, and then we started looking at where the problem comes from, and looking at doing a derivative of some vector v. In that example, it was r from A to B. So any vector we want to take a derivative of in frame 0, if we do it component by component, it should equal this. So this is according to derivative of a product, right? So I would need to take a derivative of a rotation matrix here and the derivative of the vector itself. Okay, and we saw that this is something that we didn't take into account when doing this step. Yeah, this step was only component by component. Sorry. Component by component derivative of the vector v, and we ignored the other part. Okay, now I will dwell on that because I know it causes a lot of misunderstandings. So I will give you some examples, not examples. I will say elaborate on that on the document camera. All right, so I'll come back to this equation, all right? And we wanted to take this part, yeah, and multiply it. You know what? I'll just copy this part to the document camera. Sorry. So we have d dt r from f to 0 times v in f. Yeah, I want to check how I can shorten the procedure of doing this and also multiplying by the rotation matrix from 0 to f, because eventually I want to kind of work in frame f. I want to get everything in frame f. So what I just copied, multiplied by, from the left, by the rotation from 0 to f. Okay, so I'll copy that again. 0 to f. So I want to know what that is, yeah, and I was going and step by step showing that this is equal to the cross product between, between the angular velocity of frame f expressed in frame f and that vector v expressed in frame f. Okay, so that's a cross product. I was showing that step by step. I'm moving back here. So I started showing that step by step. Okay, we decomposed the angular velocity vector omega f into its components, right? And then we looked at what is the resulting change of orientation over some short amount of time of the axis of frame f. And then using superposition, we looked at the new locations of the red axis, their new locations after some delta t time has passed. And from there, we kind of algebraically or using some basic calculus, we went to define the actual derivatives or time changes of the red axis. Okay? And then we actually also went a bit further to relate these changes to this derivative component by component of the rotation matrix from f to 0. Okay, so what I'm going to do now is just slow down a bit and maybe give you all of these formulas, but with example of that vector RAB. Okay, just relating back to the initial example. Okay, because some people struggle with cross products, some people struggle with understanding different things. Okay, so I will just slow down a bit. Okay, let me see. Okay, so first of all, I want to demonstrate this formula. Again, I want to demonstrate this formula which we won't use much. It's just an auxiliary formula or auxiliary result that we are going to use for the later formula. Okay? I just want to demonstrate it on this example. Okay, so in this example, maybe I'll copy it. What do we have? Let me draw the axis of frame 1. So that's x1 and y1. And the axis of frame 0. I'm putting them now on the same, with having the same origin, just for visual assistance. And this angle is what? Theta. Okay? So, in our example, this F will be frame 1. Okay? I'll put that as like defined as in this example. Okay, so maybe. Okay, now we have the vector RAB, which is lying in the direction of x1, and its length is r. So this is point B, and this is point A. Okay, so VF, in our case, VF is the vector RAB. I'll put this sign over vector. So RAB in frame 1. Okay, and in frame 1, what is it equal to in its components? R0, 0, right? Okay, now what is R from F to 0? Or from 1 to 0? So this is cos theta, and here, and minus sine theta, which is the positive rotation about z. Okay, and r from 0 to f would be r from 0 to 1, which is the transpose of this one, right? So cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, 0, 1. Okay. And we also need to prepare the time derivative component by component of this rotation matrix. Okay, so d dt of r from f to 0 is d dt r from 1 to 0, which is, again, component by component. Using the chain rule, it will be minus theta dot sine theta, theta dot cosine theta, 0, minus theta dot cosine theta, minus theta dot sine theta, 0, 0, 0, 0. Okay? So I just prepared almost everything. The last thing I need to prepare is this one here. What is omega f in frame f? that would be omega 1 in frame 1, which is what? What is the absolute angular velocity of frame 1 expressed in frame 1? So it's a vector. Its direction is along the axis of rotation, okay, which is the axis coming out of the page, and is parallel to either Z0 or Z1. Put these signs here. And its magnitude is the angular rate of change, which is theta dot. Right? So how do we construct it? Simply 0, 0, theta dot. In frame 1, meaning it's theta dot units along the Z1 direction. Okay, so theta dot rotation about Z1. Okay, now all we need to do is plug in to kind of verify that it works. Okay? Okay, let's try. So let me just copy everything. So this one. Okay, so I'm copying bit by bit. So cosine theta minus sine theta, 0, sine theta, cosine theta, 0, 0, 0, 1, times the derivative minus theta dot sine theta, theta dot cosine theta, 0, minus theta dot cosine theta minus theta dot sine theta, 0, 0, 0, 0. That times R0, 0 should be equal to 0, 0, theta dot cross with R0, 0. Okay, so you can see how this is going to be a longer computation than this. Okay, so let's do that. Sorry if it's boring. I'm trying to ground you on roughly who are the players that we are dealing with. Okay, so here we got cosine theta, sine theta, minus theta dot, yeah, and here theta dot cosine theta sine theta. So added, and the 0, overall it's 0. Can you see? Okay. And then we have theta dot times sine square and theta dot cosine squared. Okay, so overall it's just theta dot. Okay, and 0. And then here we have minus theta dot cosine square minus theta dot sine square. So it's minus theta dot. Okay, and here it's sine cosine times theta dot and minus sine cosine times theta dot, 0. So overall it's 0. Okay, and I think all the rest are zeros. You can have a check. Times R0, 0, and that should equal the cross product. Okay, so far? So how to do the cross product? I'll just maybe I'll do it. I'll show you how I'm doing it. So if we have two vectors, A cross B, and I need to do A1, sorry, I'll do it AX, AY, AZ. I'm keeping it vertical. I know there are different, let's say, styles of doing that. I keep it vertical to not have to write anything aside. Okay, so I'll show you how I'm doing it. Bx, by, bz. So for the x component, yeah, I'll prepare it like this. For the x component, I'm focusing on this bit, yeah, and I'm going in this direction. So starting from here, kind of like this, with a minus for this one. So ay bz minus az by, or by az. All right? Now for the y component, don't get mixed, all right, because the direction is a bit different. For the y component, I'm looking at these bits, yeah, and I'm doing the opposite direction, like that. Okay, with this one is the minus, okay, the last one. So it will be az bx minus ax bz, okay? And the z one, okay, I'm already lazy, so for the z one, I'll go like this. Oh, no, other way. Yep. Okay, so ax by minus ay bx. Okay, so that's in general. Practice it. In this subject, you'll practice it a lot. Okay. Okay, so moving on. This should equal 2, and let's do this product here. So for the x component, we have 0. Okay. For the y component, what do we have? R theta dot. And for the z component, we have 0 again. Okay? Now, is it the same case here? I forgot the minus. Sorry, what did I do? No, it's fine. It's fine. So, wait. Yeah. Yeah. Yeah, all good? Oh, good. Okay, so this was like a lengthy demonstration of this thing here on our example. Okay? Any questions? Any questions, guys? So you may wonder, why do we need that, right? So okay, so I'll jump a bit forward. First of all, this slide is a demonstration of how we are getting from matrix multiplication to a cross product, okay? And I told you, please evaluate this and evaluate this and observe that it is the same. Do you need me to do that, or you trust me? Okay, good. Okay. So we showed this thing, okay, and then from this we are going towards our final formula, okay. So in order to get our final formula, I don't want to keep all the results in frame 0. Okay, I'm starting from this one, this formula here. Okay, is this formula fine with you guys? Yeah, so this is the time derivative of a vector in frame 0, which by our assumption is a stationary coordinate system, okay, not a rotating one. And this derivative of component by component correctly represents the actual time change of that vector v. Okay? Now what we want to find eventually is not the derivative in frame 0, but the derivative kind of directly in frame f, that other rotating frame. So what we are going to do is multiply this equation by the vector, sorry, the matrix from 0 to f, rotation matrix from 0 to f. Okay, and then on the left-hand side, we will get v dot. Yeah, so this is v dot in frame 0. We will get on the left-hand side v dot in frame f. Okay. I'll come back to that in 2 minutes. We will take the 2 minutes silence now. Sorry, guys. All right. Thank you. I guess part of your education is how to be people before you are engineers or whatever, just good people. No need, thank you. Okay, let's go back. Sorry for the rush transition. Okay, so what are we doing? Don't worry, by the end of the lecture it will get clearer. What are we doing? Let me copy this equation to the document camera. You can copy it as well, because I want to work a bit slowly with you guys. So. Okay. So where are we headed? We are headed towards obtaining v dot. I will explain in detail what do I mean by v dot. V dot is the actual time change. I will write it like that. V dot, we would define it as, say, v at t plus dt minus v at t dividing by dt. Or maybe I'll put it as delta t. And sending this delta t to 0. Okay, so in terms of pure change change over time, that takes into consideration everything. Okay, and this v could be any vector. Okay, so I want to get this change over time when my starting point is v in frame f, and my end point is v dot in frame f. And I showed you how taking component by component derivative is not going to work, because it doesn't take into consideration the hiding change in time of the rotation matrix, kind of hidden inside that v in f. So instead of representing v in 0, doing the derivative in 0 where it works, and bringing it back to frame f, we are going to do like a straightforward formula how to do it in frame f straight away. Okay, so going this step by step, first, where this one is kind of working, this one is v dot in frame 0. Okay, this is accurate because here in this 0, no change over time is hiding, because the axes of frame 0 are still, they don't change over time. They don't rotate anywhere. Okay, so the component by component derivative is actually that v dot in frame 0. Okay, so in order to get v dot in frame f, which is what I want to multiply v dot in 0 by the rotation matrix from 0 to f. Okay, this is also going to work because we already trust the rotation matrix to correctly rotate vectors. Okay, so multiplying this entire equation, this one, by r from 0 to f, what are we getting? R from 0 to f, r from f to 0. Then component by component derivative of the vector in frame f straight away, plus r from 0 to f times the component by component derivative of the rotation matrix from f to 0 times v in f. Okay? Now, these ones here together, what is this? Sorry? Sorry? They cancel each other matrix way, so this is just the identity matrix, yeah? This is 1, 1, 1, and zeros outside the diagonal. Because they are, if you remember, they are not just the transpose of each other, but also the inverse of each other. So together multiplied, they give you just this. Okay, so we can kind of ignore that. And so let me copy just the component by component derivative of the vector itself, and then plus, and all of this thing, we just worked on that one. Remember with that formula? Yeah, so this is it. Yeah, so instead of all of that, yeah, I'm going to just copy this one. All right? This is why we did all that thing. Okay, so plus omega f in f cross with vf. Okay. Now, you have a confusion that repeats every time. What is the difference between, well, let me just copy the starting point here, v dot f. What is the difference between this term by term or component by component derivative of the vector f and the dot of the vector v, sorry, the vector v? What is the difference? Well, this v dot is the true change over time. This is so this v dot is like this, true change over time, that takes into account all the things that change over time. Okay? And this one is looking at the components of the vector v when it is expressed in frame f, and for each of these components taking its time derivative, okay, as a time derivative of each of the scalar components, the x, the y, the z components. And the meaning of that physically is if you are sitting on frame f and you are kind of unaware of your own motion with frame f, you will perceive, you will think that the vector v is changing by this amount. Okay, so in the example that we did here, if you are sitting on frame 1, you are thinking that point B is not moving. Okay, you are thinking that you are thinking incorrectly that the velocity of the vector AB, or the change over time of AB, is all zeros, because you don't see its motion in this case. That's why that first component in this example, that first term was all zeros. Okay, if you just take the component by component of this vector, yeah, if you do d dt of vf, you get all zeros. Okay, this is because if you place a camera to move together with frame 1, you will view no change in the position of point B relative to A. But it is not true that point B doesn't move relative to A. So the velocity of point B relative to A is not 0. And the velocity of point B relative to A is this v dot. Okay, v dot. And if I want to express v dot in frame 1, I will get this r theta dot this is what we got. So r theta dot, I'll show you the substitution. Yeah, so maybe I'll stop again for the example. So if I want to do RAB dot in frame 1, I will need to do this ddt of R00, yeah, which is RAB in frame 1, component by component, plus the angular velocity of frame 1 expressed in frame 1, which was 0, 0 theta dot, cross with the vector itself, R00. So that's omega 1 in frame 1, and that's RAB in frame 1. So just maybe compare to this formula. I just substituted, okay? And the result here, because this is all zeros, yeah, the result is r theta dot, which means r theta dot along the y1 component. Okay, going back to the drawing. This is the y1 direction, yeah? So this would be the vector of the velocity this vector here is RAB dot, okay? And if I want to express it in frame 1, this is what it will be. If I want to express it in frame 0, we already started with that one. Okay, I'll show you maybe. Maybe before I continue, let me just say that instead of this ddt, I will be using the prime, okay? The prime instead of this, because this will be a bit confusing. This one means component by component derivation. Okay, so this is not the true change over time unless you are working in frame 0, a non-moving frame. This is not the true change over time. This is the perceived change observed by someone within the frame, okay, moving together with the frame. Okay, so this is like how the vector itself changes within the frame, and this takes into account the change of the frame itself, yeah, the change in time of the axis of the frame. Okay, and this one here is the true derivative over time. Maybe I'll write it. True derivative over time of V expressed in frame F. Now, this formula, let me copy it. V dot F equals V prime in F plus omega F cross V in F. So this is the vector itself. This is the absolute angular velocity of the frame, okay? Of the frame. So there is no connection, no physical relationship between the absolute angular velocity of the frame and the vector you want to take derivative of. It's just that you are doing that derivative. If you are doing that derivative in frame F, you will use omega of that frame F. Okay, so for instance, if you want to, let me give you, let's do some examples. So we already did one example. That was when, maybe I'll just show you that example. Yeah, so this is one example, yeah, what we just did. Is this example clear, guys? Yeah? Maybe just let's check that if we are interested in RAB dot in frame 0, can we take this one and pre-multiply by the rotation matrix from 1 to 0? Yeah, what will you get? So this will be like that. So what's the result? So minus r theta dot sine theta and r theta dot cosine theta and 0, right? Okay, so this is one way to get there. Is it matching what we had before? So let's see here. This will be the other example. If I want to work out the derivative of RAB in frame 0, can I apply this formula? Yes. So in frame 0, we will have the term-by-term derivative. Yeah. Maybe I'll keep it with a prime. So we have term-by-term derivative of the vector. What was the vector RAB in frame 0? R cosine theta, R sine theta, and 0. Okay, just a reminder. Yeah, in frame 0, like that. R cosine theta and R sine theta. Okay, so this is the vector in frame 0. And then plus, we need to have omega 0. So the angular velocity of frame 0, the absolute angular velocity of frame 0 is 0 because it's not rotating anywhere. Yeah, and cross with this one. So r cosine theta, r sine theta, 0. Okay, so this one will obviously cancel, right? And so we need to take the term-by-term derivative of this one, component by component. So it's minus r theta dot sine theta, r theta dot cosine theta, and 0. Okay, just like this one, I hope. Okay? Okay. Let's go back to the slides. Are there any questions so far? You're smiling like there are 10 questions and you don't know where to start, but don't worry. We'll do a lot of examples afternoon. So I'll just summarize here what I did. This is where we arrived. Okay, you can revise using these slides. This is where we arrived. I just showed you slower on the document camera. And this formula, I always ask, how would you call this formula? We need to give it a name because we are going to use it a million times. All right. So officially, you can call it the formula for a derivative of a vector in a rotating coordinate system. Okay? So I just shortened it to the golden formula because I'm going to use it a lot, okay? And students seem to like the golden formula. Okay, so this is it. This is the golden formula. Let me know if you have questions about it. Now this is just simply what we did, okay? Go through that. It's the same as what we did, okay? Okay. I'll see you afternoon. Thank you very much. Sorry, let me first pack it off. Do you have free time?
I have a lecture.
Okay, really quick.
Yeah. Why equal to this while this didn't equal to this?
Yeah, because in frame 0, the axis
Frame 0 is
stationary. Yeah, so yeah, it doesn't rotate. Whereas frame F rotates.
all right.
So if we do, so this is the example. Yeah, so in here I'm showing like this is wrong. If I'm taking term by term derivative in frame 1 or a rotating coordinate system, I'm not getting the true change over time because I'm ignoring the
Rotating all.
rotation of the axis. Yeah.
Alright, thank you.
I will repeat as well. Why is the omega f in f is 0, 0?
Because your f in this example is 0, right? Frame 0. In this example,
Yeah.
your f
Yeah.
is 0, right?
F is.
And 0 is
stationary.
fixed,
Yeah.
stationary. Yeah, so no motion.
Sorry, Professor, I have a question on the meaning of this one. About the definitions, the name of this function. I'm confused. What's the difference between this one, and this one?
This is okay. Normally this and this. Sorry. Normally this and this are the same in terms of notation out there, you know. But in our subject, we are taking derivatives of vectors in rotating coordinate systems. So we need to distinguish two types of calculations. One, which is taking the time derivative of each component, yeah, and the other thing is a derivative which is a physical change over time. So this will be the physical change over time. This thing. Thank you.
I'll leave it at my office. I don't know the keys, okay?
Thank you. This one.
Sorry, guys. Sorry.
Thank you so much.
Thank you. No, that's all right. But in the slides,
Yeah.
when you run this one,
Look, this is not really quick. This is not really quick. You will need to come to my consultation. Oh, you guys, you have a lecture right now? So why did you come to see me yesterday?
Because I had clubs the other days. So,
You what? Calls?
I had like
You were sick?
I had planned stuff those days.
Okay, never mind. You guys come with me. Okay, I need to be there.